Okay, today we're going to be talking about one-to-one functions. So just as functions are a special kind of relation, one-to-one functions are a special kind of function. So we'll start by defining one-to-one functions, and then we'll look at all the different multiple representations we have had of both relations and functions. We'll be able to look at those types of representations and say, is this a relation? If it is it a function? If it is it one-to-one function? So those include things like set notation, tables, arrow diagrams, verbal descriptions, Cartesian graphs, formulas and equations, and so forth. So let's start by doing a little bit of review here. Define these following terms: relation and function. Okay, you should remember that a relation is defined to be a set of ordered pairs, and then a function is a relation in which no two of its ordered pairs have the same first coordinates. What's the natural next step? We have a relation, it's a set of ordered pairs. A function is a relation in which no two of its ordered pairs have the same first coordinates. What's the natural next step? A one-to-one function is defined to be a function in which no two of its ordered pairs have the same second coordinate. So what do we've got? We've got a relation, it's a set of ordered pairs. If it's a function, no two of the first coordinates are the same. And if it is a one-to-one function, in addition to all those other things, it has no two of its second coordinates the same. A one-to-one function is also sometimes called an injective function. So a person who called an onto function surjective will call a one-to-one function injective. We'll probably won't use surjective and injective much here. Just throw those in for reference. We'll probably be calling those onto and then one-to-one. A one-to-one function is a relation, so it's a set of ordered pairs. So it still has all the properties of a relation. A one-to-one function is a function, so no two of its ordered pairs have the same first coordinate. In addition, a one-to-one function has no two of its ordered pairs with the same second coordinate. So notice that a one-to-one function must be a function first. So we must check to see if it's a function before seeing if it's one-to-one. That's sort of like saying it can't be dark blue unless it's blue. Okay? It's kind of obvious that a one-to-one function must be a function first, but notice that we must check to see if it is a function first. For example, somehow, whatever, depending on the representation that we're looking at, we have to check to see that it's a function first. And then only if it's a function, then we do even look to see if it's one-to-one. So, relations are our biggest set that we've been looking at. Then we have special class relations called functions, and a special class of functions called one-to-one functions. So, as we did with relations, and then again with functions, we've looked at them in many different representations, and we're going to notice that as we go through these different representations, we will be able to tell if it's a one-to-one function or not. Keep in mind the definition, and we can see how to apply it. Okay, so let's start with just some set notation, ordered pairs here, and determine if each one of these is a function. Well, let's first determine if it's a relation or not. If it is a relation, is it a function? And if it is a function, is it a one-to-one function? Okay, and then in general, how do we do this? So go ahead and take us a couple of seconds to do this and then come back. Press pause now. Okay, let's take a look at these. The first one is a perfectly fine relation because it is a set of ordered pairs, but it is not a function because there are two ordered pairs with the same first coordinate. That's exactly what's not allowed for a function. So if it's not a function, it's certainly not a one-to-one function or any other kind of function because it's not a function. Look at the second one there. The second one is a relation because it's a set of ordered pairs. Now, is it a function? Well, let's look and see if the first coordinates are all different. I see 1, 6, 5, 3, and 11. Those are all different numbers, so it is a function. But it's not one-to-one because two of the ordered pairs have the same second coordinate, that is a 4. The last one, the third one there, is an example of a one-to-one function. It's a set of ordered pairs. All of the first coordinates are different. 1, 4, 5, 7, and 9 are all different. And all the second coordinates are different. 2, 4, 7, 9, and 6. They're all different. Now you can have a first coordinate and second coordinate the same from one point to a different one, or even in the same one like the 4, 4 there, but you can't have any repeats of the same first coordinate in two different ordered pairs. That would make it not be a function, and also for one-to-one it can't have any repeats in the second coordinate. So what does it take to make a relation a one-to-one function? First, it's a set of ordered pairs. That makes it a relation. Second, no two of the first coordinates are the same. That makes it a function. And third, no two of the second coordinates are the same. That makes it one-to-one function. But notice, just the fact that it has no two second coordinates the same does not make it a one-to-one function. It's got to be a function first. So let's do the same thing here, but look at this in tabular form. Which of these are relations? Which of these relations are functions, and which of the functions are one-to-one? Okay, let's take a look at this and see. This first one is a relation, but not a function. Notice that the two 6's there are repeated on the inputs, so it's not a function. It is a relation because it does represent a set of ordered pairs, 3, 2, 6, 5, 5, 5, and 6, 8. But it's not a function because of the two 6's repeating. The next one is a one-to-one function. No repeats in the first coordinate, no repeats in the second coordinate. And the last one is a function, but it's not one-to-one because of the repeats in the two 5's that you see there in red. Two second coordinates the same. So how do we determine if the table of a relation represents a function or not? Well, it should have a row or column for the inputs and another for the outputs. That makes it a relation. Scan the row or column for that puts the inputs in there. So the first row or first column. If there's a repeat, then it's not a function, and thus it's certainly not a one-to-one function. If they are all different, then it is a function. Only then scan the output row or column, and if they are also all different, then the function is a one-to-one function. If not, if there's a repeat, it's still a function, but then it's not one-to-one. Notice we don't even look at the second coordinates until we've looked at the first coordinates. Okay, here's some arrow diagrams. Now, what's in pink is supposed to be the domain, and what's in purple is supposed to be the range. And are these, first of all, does it really represent a relation? If it does, is it a function? And if it's a function, is it one-to-one? Go ahead and examine these. Come back in a second and we'll check it. Press pause now. Okay, we're back. Let's take a look and see. This first one's not a relation. Why not? Well, let's see. Well, the 3 is supposed to be a first coordinate, but it doesn't have a second coordinate. So that's not a relation. That doesn't really generate ordered pairs. The second one, top right, that's a function, but it's not one-to-one. Every input only goes to one output, so that's not only is it a relation, that we actually have ordered pairs here. Everything in the domain is actually a first coordinate, and it has a second coordinate that goes with it. Everything that's in the range is really a second coordinate, so that's appropriate. But it's also a function because every first coordinate only goes to one second coordinate. Every input only has one arrow coming out of it. But it's not one-to-one because actually we have two things going to 1 in one spot. We have both 3 and 5 going to the one number 4 on the output. So that's a repeat in the second coordinate. That's the ordered pair 3, 4 and the ordered pair 5, 4. So those two 4's there, that 4 used twice, or two arrows coming into 4, makes it not be one-to-one. The lower left, that's a relation but not a function, and the reason it's not a function is because the 9 at the bottom is going two different places. So that's a repeat in the first coordinate. That's not a function, so it's certainly not one-to-one. The last one is a one-to-one function, lower right-hand corner. Every first coordinate goes only to one second, and every second coordinate only comes from one first. So what makes it a one-to-one function? First of all, there have got to be ordered pairs. That makes it a relation. In addition, every arrow coming out of a point, or every input here has to have only one arrow coming out of it, exactly one. And in addition, every output over here has to have exactly one arrow coming into it. That makes it one-to-one. So for the relation to be one-to-one function, every input must have exactly one arrow coming out of it, so that each input only goes to one output, makes it a function. And every output has exactly one arrow going into it, so that each input only goes to one output, and each output only comes from one input. One-to-one function is also sometimes called a one-to-one correspondence. Alright, let's look at some given by some verbal rules here. We looked at some of these types of relations before. Are these generate sets of ordered pairs, so they're relations. Are they functions? And if they're functions, are they one-to-one? Go ahead and work these out and come back when you're done. Press pause now. Is the biological mother of is not a function, since there is at least one person who is the mother of two different children. For example, Joy Jackson, Jack Jackson, and Joy Jackson, Michael Jackson, because that's my mother and me, and my mother and my brother. So she's used as a first coordinate more than once. Even if she was the only person in the world that ever had two children, that would be enough to make this not a function. But of course, there are many others that have many other mothers who have had more than one child. Was born in the year. This is a function since each person is born in only 1 year. So every input has only one output, but it's not one-to-one since there were two people born in the year 2012 or more. Actually, a lot more. So if there's even 1 year that we had two or more people born in that year, that would make it not be one-to-one. Is less than is not a function since 3 is less than 4 and 3 is less than 5, so 3 is used as the first coordinate twice. Is in the same fraternity as is not a function because I can be used as a first coordinate more than once, including related to myself and to some of my fraternity brothers, for example. Is the current national chief executive of is a one-to-one function since each national chief executive holds this office in only one country, and each country has only one such official. How do we tell if a rule generates a one-to-one function? A rule generates a one-to-one function if and only if each input is assigned to exactly one output and each output is generated by exactly one input. Now let's think of some of these as processes. So one-to-one functions, or maybe these are relations that are given a process. Is this process produce a function? And if it's a function, does it produce a one-to-one function? So here, remember, we're thinking of it in terms of starting with an input and transforming it into an output. Take the input and add 3 to that to get the output. That's the first one. Is that a function? Is it one-to-one? Okay, and so forth. So I'll let you read through these. Take a few minutes to do this, and then come back. Press pause now. Okay, now that we're back, let's take a look at these to see what we've got here, and see if we can explain why. I don't have the explanations written down, but we can kind of go over them. Add 3 to the input. That's a one-to-one function. Now, why would that be? First of all, why is it a function? Well, every input has only one output. When you add 3 to a number, there's only one number you're going to get out for any particular input. Okay? But also, it's one-to-one because every output only has one number that came from it. So, the number that's 3 less than it is the one input that goes to it. Okay? So, for example, you start with 2, you add 3, you get 5. Well, the only way you can get 5 by adding 3 is to start with 2. And every single place is like that, so it's a one-to-one function. The next one is also a one-to-one function. Add 2 to the input and then multiply this sum by 4. That's a one-to-one function. Every input goes to only one output, but every output comes from one input. We can sort of reverse the process to go backwards and see that there's no choices along the reverse direction, just like there's no choices along the forward direction. Move 2 steps forward. That's a one-to-one function. If you start at a particular location, you go 2 steps forward, you end at a particular location. That's one-to-one. But the only way you can end up at that particular location is to start 2 steps behind it. And so that's a one-to-one function. Translate a geometric figure 3 units to the right. Similarly, that's a one-to-one function. Because, again, the only way you can, if you start with a particular geometric figure, you're going to end up with one specific output figure, which is 3 units over to the right. And if you start with the image, the final point, the output, and look at that image and say, well, where did it come from? Well, it came from something that had to be 3 units to the left. And so there's only one input that will give you that output. Choose a city in Arkansas and go there. Well, that's not a function, because if you think about the initial point is where you start and the destination point is where you end up, but we get to choose the city, then we could start, say, in Fort Smith, and there's lots of places we could go. So Fort Smith would be used many times as a first coordinate, so it's not a function. Paint it blue. This is exactly what's a perfectly fine function, but it's sort of the opposite of what's one-to-one. If you take what happens? We start with a black box. What do we end up with? A blue box. We start with a yellow box. We end up with a blue box. We start with the orange box. We end up with a blue box. We take the blue box at the end. Do we know what color it was to start with? No, it could have been anything. And so notice that when we have a function, once we specify the input, we know exactly what the output is. But if it's one-to-one, in addition, we can look at the output and know where it came from. We know what the input is. And so we look at this blue box, we don't really have any idea what it was before we painted it. So that's absolutely not one-to-one. Reading something, so that's definitely not a function, because one person can read more than one thing. So a person might be first coordinate several times. Reflecting a geometric figure about the x-axis is a one-to-one function. Finding a number whose square is the input is not a function. So let me make sure we understand that. The input is the square of the output. So 4, 2 and 4, -2 are both points on that, so that's not a function. Rotate a point 180 degrees about the origin is a one-to-one function. So how do we determine if a process produces a function? Well, if the process never includes more than one possible outcome from a step, then it has to be a function. But if in addition the reverse process is also a function, then that's a one-to-one function. In a function, knowing the input completely determines the output. In addition, if it's a one-to-one function, knowing the output completely determines the input. So now let's look at some functions or relations given by graphs, Cartesian graphs, and we're going to determine, first of all, if it's a function or not, and if it is a function, is it one-to-one. How about this one right here? Well, this is not a function because it fails the vertical line test. We can draw a vertical line like the one I've got drawn right here at x = 9, this solid line here, and notice it crosses the graph at these 2 green points. And since, what do those 2 points have in common? They have the same first coordinate, so that's not even a function. So certainly this is not a one-to-one function. Is it true that there's no duplicates in the second coordinate? Yes, it is true on this one, but that's irrelevant because it's not a function. It has to be a function first before you see if it's a one-to-one function. This one is a function, but it is not a one-to-one function because there's at least one horizontal line that touches the graph in 2 or more points. For example, if we go up here to 5, 6, say to 7, and draw a horizontal line at y = 7, it's going to cross the graph at a point over here, if you can see my little cursor moving around there, and also over here. And so we get 2 ordered pairs, both with the same second coordinate. So it fails the horizontal line test. So this one's a function, but not one-to-one. How can we tell if a graph in a Cartesian plane represents a one-to-one function? Well, it's a one-to-one function if and only if it passes both the vertical line test and the horizontal line test. Remember, the vertical line test says that we take any vertical line, so we just take a vertical line and sort of move it across the graph, and any one of these lines that we draw either has to miss the graph altogether or cross it in exactly one point. Of course, you get a different horizontal line may cross at a different point, but there cannot be a vertical line that crosses, even one vertical line, that crosses it in two or more points. If it does, then it's not a function. So if they're all different, it only intersects the graph in one point or not at all for any vertical line, then it's a function. If in addition it passes the horizontal line test, do the same thing with horizontal line. If it touches in two places or more, then it could be still a function, but it's not one-to-one. Okay, so any horizontal line must touch it in exactly one point or not at all, and any vertical line must touch the graph in exactly one point or not at all. Has to pass both the vertical and the horizontal line test. Passing the horizontal line test alone does not make it a function. It has to pass the vertical line test to make it a function, and then pass the horizontal line test in addition to make it a one-to-one function. So check the vertical line test first, and then if it passes that, then and only then you can check the other one. Okay, so let's take a look at these graphs here and tell me which ones are, first of all, which ones are functions, and if it's a function, is it a one-to-one function? They do represent a set of ordered pairs in the plane, so they do, it does represent a relation. Okay, so take a couple minutes to do this and then come back when you think you got your answers. Press pause now. Okay, so this first one is a one-to-one function. It almost kind of looks like it might level out right here, but it's actually increasing the whole way. It is kind of, the rate of increase kind of slows down through here and then picks up speed later. But it passes both the vertical and the horizontal line test. B is a function. It passes the vertical line test, but not the horizontal line test. For example, the x-axis touches the graph twice. C is actually a one-to-one function, although I can see where this would be hard to tell. This is not truly vertical here. It's actually what we call an asymptote. So it's actually increasing very, very rapidly right here, but not vertical, and then kind of levels out a little bit as it goes on. It actually increases forever, but not so, but very slowly. So this is actually a one-to-one function. It almost looks like it's not even a function because of what it looks like vertical. If it really was vertical here, it would not be a one-to-one, but it's not truly vertical. D is a function but not one-to-one. It passes a vertical line test but not the horizontal. E is a truly vertical line. Well, it's a relation, but it's not a function at all. F is a relation but not a function. Fails the vertical line test, so who cares about the horizontal line test? G doesn't pass either the vertical or horizontal line test. That's a relation but not a function. H is a one-to-one function. Passes the vertical and the horizontal line test. And I is supposed to be a horizontal line. That's a function, but it's not one-to-one. In fact, everything goes to 1 for that one. Alright, so how about an equation or formula? Let's look at these equations here and tell if it represents a relation. Well, first of all, they're all relations because we just have two letters there that represent, so this generates a set of ordered pairs, so it's a relation. But is it a function? And if it is a function, is it one-to-one? Then how can we tell just by looking at the formula? Okay? Figure these all out. Press pause now. Okay, let's take a look at these. Well, remember, if you can solve for y in one single equation, it's a one-to-one function. In fact, these are the same examples we looked at in our last video on functions. So y equals x plus 4, that is a function because it's already solved for y. But if in addition we can solve for x in one single equation, which this one we just subtract 4 from both sides of the equation, to see that x is y minus 4, that's going to make it a one-to-one function as well. So y equals 3x plus 2 is already solved for y, so that's clearly a function, but we can also solve for x by subtracting 2 and dividing by 3. That is, subtracting 2 from both sides of the equation and dividing both sides of the equation by 3, and we find that x is y minus 2 with the quantity divided by 3. And so that is solving for x in a single equation, and we could solve for y in a single equation, so that is a one-to-one function. The next one's already solved for y, but notice something happens here when we try to solve for x. We we add 6 to both sides, we get y plus 6 equals x squared. But when we try to solve for x, we get plus or minus the square root. So x is the square root of y plus 6, or x is the square root of the minus the square root of y plus 6. And so that's not one-to-one. Notice that we should be able to put in something here. For example, y is 3. We get 3 plus 6 is 9. Square root of 9 is 3. So there's 3. And this other one here, we put in 3 for y. 3 plus 6 is 9. Square root of 9 is 3. Then we have a minus out front, so that gives us an x of negative 3. So that generates the order pair negative 3, 3, and the order pair positive 3, 3 repeat in the second coordinate, not a function. Or not, it is a function, excuse me, but not one-to-one. The next one has the same problem, but this time it's on the x side. So when we try to take the square root of both sides here to solve for y, we get y square root of x, or y equals minus square root of x. And so here we see that we get repeats in the first coordinate, so it's not even a function at all. It's okay relation, not a function. And of course, certainly if it's a function, not a function, it's not a one-to-one function. The next one, f is 9/5 c plus 32. Solve for c. You do subtract 32 from both sides and then multiply by 5/9. And yeah, we can solve for c in one equation. We solve for f in one equation. It is a one-to-one function. The next one is not solved for x or y, but we can solve for y, so that makes it a function. But we can also solve for x in one single equation, and so that makes it a one-to-one function, the fact that we can solve for both variables. The next one, being solving for y, involves taking a cube root. It's an odd root, so there's no plus or minus involved there. So we can solve for y in one single equation. That is a function. But when we try to solve for x, it involves a square root. An even root introduces a plus or minus. And so we see that there are two possible outcomes for many of the two possible inputs for the same output in many cases. So for example, let's see, what's an easy one? One that works out nicely here. Let's see. Okay, let's put in y is 2. 2 cubed is 8, minus 4 is 4, the square root of 4 is 2, so that generates 2/3 for x. So if x is 2/3, y is 4. But we also see over here that when x is, when I put in y is 4, I can get x is negative 2/3. So x is negative 2/3 gives us also y is 4. And so that's not a one-to-one function. It is a function, but it's not one-to-one. The next one, when we try to solve for y, we get the plus or minus thing going on again, which is really just a shorthand notation for two equations. And so, once again, we get something that's not a function. And y equals 4, that is a function, but it's not one-to-one. All the y's are 4. We get lots of repeats in the second coordinate. In fact, they're all repeated. So it's not one-to-one, but there are no repeats in the first coordinate. We can pick anything we want for the input. We always get 4 for an output. So it's a function, but not one-to-one. But whereas x equals 5 is a relation that's not even a function, because as we see there, all the x's are repeated. So how do we tell if an equation in two variables represents a relation? And how can we tell if it's a function and if it's a one-to-one function? Well, if the equation can be, first of all, any equation in two variables represents a relation. If it can be solved for the variable representing the second coordinate in a single equation, that makes it a function. And then if it can also be solved for the variable representing the, that should say first coordinate, then it represents a one-to-one function. You have to be able to solve it for both the first and the second coordinate That's a typo. That should say first coordinate there. So after studying this material, you should be able to define a one-to-one function, determine and also be able to determine if a relation is a one-to-one function in any of the possible representations we've looked at: sets, notation, tables, arrow diagrams, verbal descriptions, Cartesian graphs, formulas and equations. In fact, some of the other ways maybe that we didn't go over in this video, you should be able to do them as well. Okay, so we started with relations. Special kind of relations are functions. Special kind of functions are one-to-one functions.